Okay, this is the last summary about the nanoelectronics. The chapter is the flash memory. The first is the position of the flash memory. We can see um, last this time DRAM, but the flash memory has a non-volatile characteristic, so it can save the charge to the gate. And also we can use this data storage or database. So this flash memory is billion or trillion trans flash memory into this our computer, and it can build the database. And the evolution about the flash memory. The first, we can use the planar structure, so floating gate, and this to the now we can use the 3D structure. We can call the virtual flash memory. We can step by step to the vertical direction. So we can improve the integration and the speed or anything else is a improvement. And we can see the evolution about the flash memory in 3 point of view. We can see this evolution. First is the technical evolutions, and second is the structural evolution, and third is a logical evolution. The technical evolution in the verification process is going to the improvement. So we can we can make the much more scaling down device, and integration is going upper and power consumption is going down. So this is the technical evolution. And the structural evolution is the structure about the flash memory is going to first in the planar, going to the 3D vertical structure, and it can give us to integration improvement, and the much performance is fast and good, and the lower power consumption. And the logical evolution is the important thing about that. SLC means the single SLC is a I think single level capacitance. And yeah, single level cell. Single level cell means one cell by one bit. And multi-level cell and triple level cell and quadruple level cell. A cell can have a bit. Bit it is information about what we read, what we want to write. So single is 1 bit, and multi is a 2 bit, and then the triple is going to 8 bit. 000 and 010 ESC. And quadro is a 60-bit can have it to the one cell. So the information integration is going good. So we don't need the less, we don't need the much more cell to the same information. So we can save our custom and our resource, and it's going to much more integration. It's going to cheaper, and but the trade-off is their reliability is going to a little bit down. And then we can see the cell operation. The basic structure about the floating gate. the most important thing, it can have the control gate and floating gate. The control gate is a function as a controller, and floating gate is a function as a storage about the charge. And then you can see this oxide. We can call this one is the tunneling oxide, and this one is a blocking oxide. The tunneling oxide as a function as the charge to the floating gate by the tunneling. And then the blocking oxide is a function as the charge did not tunneling to the control gate because this is the leakage current, so it can much more power consumption go much high power consumption, and the operation performance is going down. And then the most important thing is the oxide thickness. The tunneling oxide, it can possible to the tunnel to the floating gate, and it can impossible to the blocking to the charge to tunnel to the body because this is the leakage current, so we can prevent this happening. So we choose the thickness the 2 or 3 nanometer about the tunneling oxide. And then this is the writing operation arrangement diagram. The charge that through the tunnel to the floating gate. And then erase the enrichment. The bias is a different bias optically. The opposite bias give to the by the writing operation. So the floating gate through the tunnel to function nodium tunneling to the body. So we can erase this information. And how we read about this transistor the state? First, we can select the read bias. The read bias is a function of the key, how to read the transistor state. First is a write operation. The NAND or NOR structure flash memory. There's 2 types of the NAND or flash memory about NAND or NOR. The NAND, they use the function nodium tunneling, funnel nodium tunneling to the writing operation, and NOR gate is a use the hot carrier injection because their structure can control the source and drain. We can give the source and drain individual bias, so we can control this VDS. So we can use this hot carrier injection. But the NAND is they're much more channel share the same source and drain. So we can't control this bias. So we use the photonodium tunneling. And then the read bias first is when there's in the charge trapped in the floating gate, they need much less stressor voltage. So in the read bias, they have a much more drain current. You can see this state about the charges, which means write it. And then if they're not write it, they're in the read bias, there's very much lower drain current we can see. So this is how we read the cell operation. And then this is the problem about the flash memory, the retention and endurance. Endurance is when writing or read, erase, writing, read, erase. This is called the cycling. When we doing this thing many times, we can keep the oxide or other thing is going to breaking down, so it can give a much more threshold voltage shifting to the higher, so the device is going breakable. And then retention is the when we trap the charge can trap it infinite time. So it going on depends on the time. So we solve this problem. So this time, floating gate and CTF, the charge trap press, is a difference. The floating gate has a many problem about I told you before. So, and then the size about the cell is much bigger than the charge trap flash, much bigger. So it can cost many resources. So we much advantage the charge trap CTF. So now we use the CTF transistor. And the CTF transistor structure, we use the remove the floating gate. We use a nitride because it is a good insulator and its permittivity is so good. So which means the charge is much well trapped. So this structure is called the Sonos. The Sonos is the oxide nitride oxide. It's called ONO structure. So this advantage about the CTF is much more good data retention, and gate stack is much more simpler because we remove the floating gate or and much more we make it smaller. So the size is going down smaller. So we don't need much power, so we can reduce the power consumption. And this is the mathematical modeling about these two types about the flash memory. The this is the dependent on about this ONO structure, and the CTF it can depends on about the EOT about the tunneling oxide. So this is a much more easier to control and much more specific control if possible. And then the or NOR structure, the left is a NOR and right is an AND. It has advantage. It has two types. It has the advantage and disadvantage. The NOR structure is much more metaline, so we can much more process to the make it this cell, but we can control the source and drain gauge individually, so we can much faster read out to the indoor structure. And then the NAND structure is structured by the cascade form about the sharing source and drain to the any transistor. So this advantage is the writing operation and erase operation because the writing and erase use the several transistor in one times. So and this structure is much less meta line needed, so we can improve the integration. And I told you about the multi-level. So the SLC, which means one cell can have the one bit about the information, but MLC, it can carry about the two bits, so it can state the full state. And the triple TLC, it can have 8 bit about the information in the model cell. So we can see this the VT window in the same threshold voltage window. There is a much more integrated their state about the information. So this is the problem occur concerns about the much more much control is the the much shaping the threshold voltage about the and we should have to much more controllability is going improve because if the we can poor control there's a two information we don't read the right ways because it is overlap the threshold voltage, so we don't know about what state about this. So there's a var variation is occurred in many point of view. So what we need to do is we target to the threshold voltage, and we should have two ways about to solve this problem. First is the threshold voltage window is going much wider, and but it can not ideal ways. And second way is we can much shaping the stressor voltage shape. It reduce the variation to the stressor voltage. And then this is the about the first memory and structure and operation. And now, okay, thank you for listening, and I'm done.